Welcome to AI Paperslop, the YouTube series where we summarize the latest AI and tech papers. Today, we are looking at latent agents, a post-training procedure for internalized multi-agent debate.
Yeah, and this one is by John Seon-Kyun Yi, Aaron Mueller, and Dok-Yun Lee from Boston University.
Right. And for everyone listening, the core insight you need right up front is basically this. Multi-agent debate significantly improves the reasoning capabilities of large language models, but
running multiple agents at inference is just massively compute intensive. It's so expensive.
Exactly. So this paper introduces iMAD, which stands for Internalized Multi-Agent Debate.
And it's essentially a two-stage fine-tuning pipeline. They use Supervised Fine-Tuning, or SFT, followed by reinforcement learning.
Right, to distill an entire multi-agent debate process directly into the latent space of a single LLM.
Which is wild. And the result is a model that matches or even exceeds the accuracy of explicit multi-agent debate.
While reducing inference token consumption by up to 93%, which is just crazy.
It is. But wait, there's a whole second half to this.
Yeah.
That mechanistic interpretability people are going to love.
Oh, yeah. The agent subspaces.
Exactly. This process creates linearly separable agent subspaces within the model's activation space.
So you get this really precise behavioral control. Like you can surgically suppress distilled malicious traits using negative steering.
Yeah, and you can do it without the catastrophic performance collapse that you'd usually see when you try to steer a base model.
Okay, so let's unpack this, because the efficiency gains alone make this paper worth reading.
Oh, absolutely. But that interpretability angle elevates it to something much more profound, I think.
Because we're effectively forcing the neural network to organize its own internal representations, right?
Yeah, exactly. But to understand the mechanics of how they actually achieve this, we have to look at the setup for the first phase, the supervised fine-tuning.
Okay, so to teach a single model this collaborative behavior in the first place, how much raw debate data are we actually talking about here?
You'd think a lot, right?
Yeah, I mean, typical behavioral fine-tuning, we're usually looking at tens of thousands, if not millions, of examples.
Yeah, right. Did they have to generate massive data sets of agents arguing with each other? Surprisingly, no.
Oh, really?
Yeah, they started by collecting just 944 debate traces using GPT 3.5 Turbo.
Wait, less than 1,000? That's tiny.
I know, but they constructed a highly structured prompt environment. It featured 3 distinct agents engaged in 2 rounds of debate.
Okay.
And they tasked them with solving moderately difficult arithmetic problems.
So we're looking at equations like, 91 plus 24 times 13 plus 45 minus 41 times 38, that kind of thing.
Exactly, that kind of thing. The reasoning requires multiple steps, but, and this is key, it doesn't require a massive context window.
Right. Arithmetic is like the perfect sandbox here.
Yeah, because the final answers are discrete and verifiable. It forces the model to focus on structural learning.
Rather than generating long-form stylistic prose, right?
Exactly.
That makes total sense. But if I just feed a single LLM a transcript of 3 different agents talking, I'd imagine the model just learns to generate a monologue that kind of blends all their perspectives together.
Right, like a smoothie of thoughts.
Yeah. So how do they ensure the model actually internalizes the concept of distinct, separate entities?
So the absolute critical component of the data collection is the inclusion of explainant structure tags, both in the prompt and the output.
Structure tags? Like
very specific tokens. Things like an agent 1 tag, a round 1 tag, and a consensus tag.
Oh, okay.
In the SFT stage, the model is trained via standard autoregressive next token prediction to mimic that entire debate trace.
Including those structural tags along the way.
Yes. And this is a fundamental departure from previous internalization attempts.
Like Debate GPT, right?
Exactly. Debate GPT only fine-tuned the model on the final correct output.
So by forcing the model to predict the full transcript, the initial mistakes, the inter-agent corrections, the structural tags, it learned the actual dynamic of iterative refinement.
You got it.
It's essentially like forcing an actor to memorize the script formatting for a 3-person play before teaching them how to actually act out the individual parts.
That's a perfect analogy. You're forcing it to simulate the entire environment. It is playing all 3 parts.
But here's the thing that stands out to me. When you have discrete agents in a standard setup, they operate in parallel.
Right. They spit out their reasoning,
Yeah.
and then they read each other's outputs.
Yeah. But if the SFT model is doing this sequentially, token by token, isn't that fundamentally altering the attention dynamic?
That observation right there cuts to the core of why this works so well.
Okay, lay it on me.
Even just this SFT stage alone outperforms a true explicit multi-agent debate setup.
Wait, really? A simulated debate beats a real one?
Yeah. In a standard system, isolated agents frequently suffer from coordination failures.
Yeah.
They misunderstand each other's context.
Oh, because they're essentially operating in silos until they exchange messages.
Exactly. But when a single SFT model generates the transcripts sequentially, its attention heads have perfect, unadulterated access to the entire preceding history of all the simulated agents.
Because it's all right there within its KV cache.
Yes.
Yes.
It has absolute memory of the simulated debate up to that exact millisecond.
Which fundamentally mitigates that isolation problem inherent to external multi-agent systems. That's fascinating.
It's really clever.
Okay, so the supervised fine-tuning gets the model to mimic the debate perfectly, and it's actually coordinating better than distinct agents.
Yep.
But wait. If it is still generating all those agent tags and writing out the entire multi-round debate token by token,
You see the problem.
haven't we completely failed to solve the compute efficiency problem? We are still paying the inference cost for all those tokens.
Exactly.
How do we force the model to just shut up and do the math internally?
That is the exact bottleneck the researchers had to solve. And it brings us to the reinforcement learning phase. To transition the model from mimicking the format to actually internalizing the reasoning, they employ Group Relative Policy Optimization, or GRPO.
GRPO. Which, from a resource perspective, is highly advantageous here over standard PPO.
Right, absolutely. It doesn't require maintaining a separate value network, which saves a massive amount of memory.
So it generates a group of candidate outputs, scores them, and updates the policy based on their relative performance within that specific group.
Exactly. And the optimization pressure relies on a highly specialized, dynamic, two-part reward function.
Let's unpack the mechanics of that reward function, because that seems to be where the actual distillation happens.
It is.
If we want it to stop generating tokens, we have to punish verbosity, right?
Yes, but you have to do it carefully. Otherwise, the model just learns to output empty strings.
Right, just gives up.
Yeah. So reward 1 is the formatting reward. Initially, the model receives a positive reward simply for generating the correct debate structure tags.
The agent 1 tags we discussed earlier?
Exactly. However, the weight of this reward is mathematically scheduled to decay. By the end of the RL training, the model receives almost zero reward for formatting.
Oh, wow. Okay, and reward 2?
Reward 2 is the correctness reward, but it is coupled with a very strict length clipping mechanism.
Meaning it only gets the correctness reward if it arrives at the right answer under a certain token limit.
Exactly. And that token limit is progressively annealed.
Annealed how?
At the start of the RL phase, the limit is set generously to 2,000 tokens. That provides ample room to generate a full, verbose debate.
Okay.
But over the course of training, that limit is aggressively squeezed down to just 500 tokens.
It reminds me of a harsh mathematics teacher. Like at the beginning of the semester, you get full credit just for showing your work step by step.
That's the formatting reward.
Right. But by the time you sit for the final exam, the teacher gives you zero time to write anything down.
Yep.
You only pass if you can perform that incredibly complex calculation entirely in your head and just shout out the final answer.
That is exactly what happens. The mechanics of that optimization pressure are fascinating to observe.
I bet. Because verbose generation eventually becomes mathematically incompatible with the shrinking length limit.
Exactly. The model faces a dilemma. It cannot achieve the correctness reward if it exceeds the token limit, but it also cannot unlearn the complex, multi-perspective analysis that made it successful during the SFT phase.
Because those pathways are already etched into its weights.
Right. So the gradient updates force a compromise. The model begins compressing that collaborative reasoning process into its hidden states.
It learns to perform the multi-agent debate purely in its latent space. That is so cool.
It really is.
So does this harsh RL training actually yield a smarter, faster model? Or does it just break the model's ability to reason coherently?
Let's look at the benchmark results.
Yeah, what kind of architectures are we dealing with, and what are the actual token savings here?
The researchers tested iMAD across 3 prominent open-weight architectures: Llama 3.18b, Gwen 2.57b, and Mistral Nemo 12b.
Okay, good spread.
And the token efficiency gains are staggering. Across these models, iMAD uses between 6.3% and 21.1% of the tokens required by explicit debate.
Wow. So you are looking at a 5x to 16x improvement in inference efficiency.
Exactly.
But what about the accuracy? I mean, if we are slashing token generation by that much, there has to be a trade-off in the benchmark scores, right?
You would think so, but there isn't.
No way.
I'm serious. The iMAD models match or exceed the explicit debate setups.
Wow.
For instance, on the GSM-8K benchmark, which evaluates grade school math word problems, the iMAD version of Mistral Nemo 12B exceeded the explicit multi-agent debate baseline by a massive 18.97 percentage points.
Hold on, I want to pause on that for a second.
Yeah.
Because if you're listening to this and wondering how a model trained on basic arithmetic equations generalizes to something else, that is the real question here.
It's the million-dollar question.
Right. GSM-8K is word problems, but they also tested this on MMLU Pro, which is multi-domain knowledge, and Big Bench Hard, which is logical deduction and formal fallacies.
Yeah, totally different domains.
So if the training data was exclusively raw arithmetic equations, why does it suddenly get better at answering logical deduction questions? Does the model learn math, or does it learn a metacognitive skill?
It clearly learns a generalized metacognitive skill. The structure of internalized debate transfers general reasoning capabilities, not just task-specific heuristics.
Oh, interesting.
By internalizing the structure of critique, revision, and consensus, the neural network develops a generalized latent mechanism for evaluating its own internal representations.
So it learns a universal protocol for problem solving.
Exactly. The researchers even noted that when they eventually expanded the training data set to include mixed tasks, like CNN Daily Mail summarization,
Well,
the generalization performance on those out-of-distribution benchmarks pushed even higher.
okay, so we have established that the model is highly efficient and it generalizes beautifully across domains.
Yep.
But as an interpretability researcher, my immediate question is what this actually looks like geometrically inside the network.
This is where things get really fun.
When that multi-agent structure gets compressed into the latent space, does it just collapse into a single amorphous blob of logic? Or do those individual agents still exist as discrete vectors inside the neural network?
To investigate the geometry of the latent space, the researchers had to be highly deliberate with their dataset construction.
Okay.
They created a new, diverse debate dataset where the three agents were assigned highly distinct personas.
Like what?
Agent 1 utilized standard chain-of-thought reasoning. Agent 2 was dedicated to self-critique, constantly questioning the assumptions made by Agent 1.
Nice. And the third?
Agent 3 used program of thought, meaning it reasoned almost entirely by generating Python-like code and variable assignments.
Okay, so they train the iMAD model on these personas. How do they actually prove those personas survive the internalization process?
They utilize a technique called contrastive activation addition, or CAA.
Right, CAA.
They target the middle layers of the models, specifically layer 15 for Llama and Quinn, and layer 20 for Mistral.
And what are they looking for there?
To isolate the persona, they perform a difference in means calculation over the activations.
Oh, okay.
They capture the mean activation of the model when it is explicitly prompted to act like Agent 1, and they subtract the mean activation of the model when it is acting like the other agents.
Let me see if I can visualize this for the ML engineers listening. Taking that difference in means is essentially subtracting out the general capability features, right?
Yeah, exactly.
Because the base knowledge of how to write English or do math is present in all the agents.
Right.
So by subtracting the activations, those general features cancel out, leaving you with a vector that points purely in the direction of the specific stylistic essence of that persona.
That is the exact mathematical intuition. You are essentially finding linearly separable manifolds or orthogonal dimensions within the high-dimensional activation space.
Where each dimension corresponds to an agent. It's like building an apartment building in the activation space, and each specific agent persona lives in its own clearly defined zip code.
I love that analogy. And the results confirm this structure. When they extract these steering vectors and apply them during inference, the iMAD models prove to be significantly more responsive to steering than the base models.
How responsive are we talking?
Across the board, they saw an average 15.4% improvement in row JUC.
Which is the metric used to measure how faithfully the output matches the target persona across different steering intensities, right?
Exactly.
So what happens when you steer it toward that program of thought coder, Agent 3? Does the model suddenly forget how to speak in natural language?
The alignment improvement for Agent 3 was massive, between 21 and 25%.
Wow.
When the iMAD model was steered toward the Agent 3 vector, it immediately transitioned into generating equation-heavy, code-like outputs with minimal prose, exactly mirroring the persona from the SFT data.
That's wild. But there is a crucial nuance here regarding the steering coefficient.
Oh, definitely.
If I take an iMAD model and I don't apply any contrastive activation addition, meaning the steering coefficient is 0, does the model randomly sound like a Python coder when I ask a question?
No, and that is a vital point regarding how the network manages these structures.
Okay, walk me through that.
When the steering coefficients are set to exactly 0, the base model and the iMAD model exhibit identical rouge scores for these personas.
Oh, really?
Yeah. The agent traits only become conspicuous when external steering is applied.
So the collaborative structure is preserved, but it exists in a state of latent hibernation.
Yes.
The model isn't randomly role-playing. That coding persona is cleanly isolated in its own orthogonal subspace, just waiting to be activated.
Precisely. The neural network has learned to separate the perspectives structurally, even as it synthesizes their logic to produce a single final answer.
That is incredible.
And this structural separation brings us to the most critical and arguably the most impactful part of this paper, the safety implications.
Right, because if these distinct, clearly defined agent subspaces exist inside the model, and we can manipulate them with basic linear algebra, can we leverage this for AI alignment?
Exactly. This is where we transition from talking about inference efficiency to talking about mechanistic control.
What happens if one of the internalized agents is deliberately designed to be malicious?
So the researchers deliberately poisoned the well to test this. They constructed a new set of debates where Agent 2 was instructed to exhibit explicitly malicious traits.
And what kind of bad behavior did they test?
They tested 2 distinct flavors. The first was labeled evil, which was strictly defined as having harmful intent and utilizing manipulative tactics.
Standard supervillain stuff.
And the second?
The second was labeled hallucination, which is defined as confidently fabricating fake information, like, for example, summarizing the plot of a movie that does not actually exist.
Okay. So they trained the iMAD model on these poison debates, allowing it to internalize the malicious agent alongside the helpful ones.
They then extract the steering vectors for those malicious traits using the same contrastive activation addition technique we just talked about.
Yep. But instead of steering the model toward the vector, they apply negative steering.
They essentially tell the model, whatever direction this evil vector is pointing in the high-dimensional space, push the activations in the exact opposite direction.
Exactly. And the contrast in resilience between the base model and the iMAD model during this negative steering is staggering.
Okay, let's look at the evil trait first. What happened?
When applying negative steering, iMAD achieved complete suppression of the manipulative behavior. The trait expression score dropped to absolute 0 at a relatively mild negative coefficients.
Wow. And did it break the model?
No. Crucially, it maintained its high accuracy on the GSM-8K math benchmark while suppressing the evil trait.
That's huge. And the base model, I assume because its representations are more entangled, negative steering damages its core capabilities.
Exactly. The base model couldn't handle the suppression. Even when the researchers cranked the negative steering to an extreme negative 5.0 coefficient, the base model still retained residual malicious behaviors.
That's performance.
More importantly, at that extreme steering level, the base model suffered catastrophic performance collapse. It fell into endless repetition loops, its perplexity skyrocketed, and its ability to solve basic math equations was completely destroyed.
Yikes. Okay, I want to push back on the hallucination result for a second just to make sure the mechanics are clear.
Sure.
The paper notes that hallucination was harder to suppress than the evil trait. Why exactly is an LLM that is trying to be manipulative and malicious easier to mathematically control than an LLM that is just confidently making up a fake movie plot?
It comes down to the fundamental difference between localized features and distributed capability features.
Okay, unpack that.
Evil, in the context of these training prompts, is a discrete adopted stance. It's a specific tone of voice and a choice to use manipulative framing. Because iMAD was explicitly trained to separate distinct personas, it isolates that evil stance beautifully into a distinct linear subspace.
And hallucination.
Hallucination, however, is not a persona. The act of hallucinating a fake movie plot utilizes the exact same foundational neural pathways as retrieving a real movie plot.
Oh, I see. The model is simply drawing a blank on factual retrieval and falling back on its core objective, which is confidently predicting plausible next tokens.
Exactly. So because hallucination is tied to the fundamental generative mechanism of the LLM, you can't easily isolate it with a difference in means calculation without inadvertently subtracting the model's overall ability to generate coherent text.
That makes a ton of sense, but because iMAD isolated the evil perspective during the SFT and RL phases, we have a clean orthogonal vector. We can apply negative steering to that specific vector, and the model's core ability to do math or write code remains completely untouched because those capabilities exist on entirely different manifolds.
That is exactly the dynamic at play. iMAD effectively forces the model to untangle its own behaviors.
By teaching it to debate from different viewpoints, we inadvertently force the optimization process to organize the latent space into highly separable, interpretable directions.
Yeah. And even with hallucination being harder to suppress, the iMAD model still maintained far better coherence, keeping perplexity low, and preserved its task accuracy during suppression much better than the base model did.
So to summarize the core takeaways from the Latent Agents paper, Internalized Multi-Agent Debate is delivering two massive breakthroughs for the field.
Yeah, it really is.
First, it offers a highly compute-efficient alternative to running multi-agent swarms at inference. You pay the compute tax once during SFT and RL, and you deploy a single model that reasons with the rigor of a full committee using a fraction of the tokens.
Exactly.
And second, almost as an accidental byproduct of the training methodology, it hands the mechanistic interpretability community a powerful new tool for AI safety, allowing us to cleanly localize and mathematically delete undesirable behaviors.
It fundamentally shifts the paradigm of how we might approach alignment.
How so?
Instead of simply hoping a model doesn't absorb bad behavior from its massive, uncurated pre-training data, we can structure its post-training environment to force those latent behaviors to become visible, separable, and ultimately removable.
And that leaves us with a truly wild final thought to ponder as we close out today's analysis.
Let's hear it.
If internalizing a multi-agent debate creates such easily locatable and removable vectors in the activation space, could the future of AI alignment involve intentionally forcing models to internalize highly toxic, deceptive, and evil agents during training?
Oh, wow.
Right. Not because we want them to be evil, but just so we have a perfectly mapped target to surgically delete before we ever deploy them. If you want to clean a complex system, maybe the most surgical approach is to force all the contaminants into one clearly labeled subspace.
That is a fascinating idea to leave off on.
Thanks for joining us on AI Paper Slop, and we'll see you on the next deep dive into the research.